Algebra 1 students, welcome to your 6.4 notes. Today we're going to look at applications of systems. It might be a challenging section for some of you. Some of you will say, finally, I understand why we're using this. So let's jump right into it. On this screen, you see the three ways that we've used to solve systems. There's truly nothing new to you there. Substitution, elimination, graphing are the three ways. But what we want to talk about is what's the real life application of these problems. So we can use systems for lots of things. We're going to look at some of them today: mixtures, rates, break even points. And we should probably start with this definition. A break even point for a business is the point at which income equals expenses. And that's going to be relevant to our first question here. A bracelet designer sells his product for $5. Each bracelet costs $2.25 to create, and there are also some startup costs of $1,485. How many bracelets must he sell for his company to break even? In other words, for him to quit spending money and perhaps even at some point starting to make some money. So to find the variables, and I always find these break even ones to be a little tricky, so I kind of do them all the same way. X is going to be with our product, which in this case would be the number of bracelets. Y is going to represent, and this is the weird variable. It's always a financial one. So I'm going to put it this way. I'm going to put it as profits or expenses. And I'm going to put a slash there because it's really for both. And the way we create systems from these has to do with that variable kind of being a little bit flexible. So let's start with this. Let's start with the profits equation. How is this company going to make money? Well, it makes money by selling bracelets, and it costs, or excuse me, they make $5 for each one they sell. Now, there are some expenses associated with that. For instance, each of those bracelets that they sell costs $2.25. And also, there's that initial setup fee of $1,485. So it's a couple of things that go into the expenses and only one that goes into the profits. And perhaps a better way to say rather than profits would maybe be to say like incomes, but I'm going to stick with this. So there's our system. Now we can choose a method to solve there. We have the three options. On the first three, I'm going to kind of use all three, and then we'll switch from there. So on this one, I'm going to use substitution. I see that y equals 5x, and here I have a y, so we'll say 5x is equal to 2.25x plus 1485. If I subtract the 2.25x from each side, I'd have 2.75x is equal to 1,485. That's just a quick step of division at this point. And so 1485 divided by 2.75, I'm punching this into my calculator right now. And my calculator tells me that number is 540. So the question was, how many bracelets must he sell? He must sell 540 bracelets. And remember, that's to break even, and every bracelet he sells after that would actually start making money. All right, on number two, we have a situation with two aquariums being filled. The one tank has 100 gallons of water already in it and is being filled at a rate of 12 gallons per minute. The larger tank already has 200 gallons and it's being filled but at a slower rate. After how many minutes will the two tanks have the same amount of water? Well, we're going to kind of walk through the same process we did on the others. We're going to define x and y. And again, you don't have to use x and y as your variables. It probably makes sense, though, especially if you're going to consider graphing to use those. So what x is going to be is the number of minutes. So it's time in minutes. Okay, and then the y variable would be the amount of water in either tank. All right, so our first tank, the 800 gallon tank, how much water's in it? Well, 100 gallons, and we're filling it at a rate of 12 gallons per minute. So we'll do 12 times the number of minutes. The second tank starts with more, but it's actually filled at a little bit lower rate. I'm going to use graphing on this one. So I'm going to go to my friend Desmos. Hi, Desmos. So y equals 100 plus 12x, and y equals 200 plus 7x. Now what I need to do here is find where they intersect, and obviously I do not have a great window set at this point, but look there and let's see if we can find it. There I see the intersection at 20 and 340. So let's go back to the problem and get that information marked down. The result, the solution there is 20 and 340. Now let's make sure we answer the question. After how many minutes will the two tanks have the same amount of water? It's 20 minutes. Now one thing we didn't answer or didn't ask was how much water would there be? Well, we know that answer, 340 gallons. All right. In the middle of winter, this is not the problem I like reading, but Mr. Hale is riding his wave runner on a river. It takes 30 minutes to travel 16 miles downstream. The trip back, when I'm going against the current, takes a little bit longer. But my speedometer shows a steady rate of speed, a constant rate of speed for both trips. How fast was the wave runner traveling in relation to the water? And how fast was the river's current moving? All right, so we actually have two things to consider. One is the speed that the wave runner is traveling, and that's in relation to the water. And then we have another variable, which would be the speed of the current. So I'm going to, the current speed. So again, that's like how fast is the river moving? How fast is the water moving down the river? Now this right here, distance equals rate times time, is really important on these kind of questions. I know in both the downstream and upstream trip that my distance was exactly 16 miles. But when I went with the current, my speed and the speed of the water are basically added together. The current's helping me. And it says it took me 30 minutes for that trip. Instead of putting in 30 for the time, I'm going to put it in terms of hours. So I'm going to put a 0.5 or a 1/2 right there. Now the return trip, still 16 miles, but this time I'm going against the current, so my total speed is going to be x minus y, or the rate as we use it right here. And the time on this trip was exactly 1 hour. All right, there's my system. Now I'm going to use elimination on this one. If I were to rewrite that first equation, I'm going to actually write it over here to the right and kind of switch the order a little bit to what we're used to. So 0.5x plus 0.5y equals 16. Here we have x minus y equals 16. What I'm going to do is multiply the first equation by 2. This one right here. And I'll rewrite it down here. 1x plus 1y equals 32. And then x minus y stays the same as 16. And look what we have there. 2x is equal to 48. So x is 24. And if I plug that value that we see there, x is equal to 24, if I plug it in right here, we can do a pretty quick calculation. 24 plus y equals 32, so we know y has to be 8. The question says, how fast is the wave runner moving in relation to the water? And how fast was the river's current? Well, the wave runner, that's my x value, would be traveling at 24, and we used miles for our distance and hours for our time, so miles per hour. Where the river current, that's the y value, so the river was moving at 8 miles per hour. So my trip one way was faster than the return trip when I went against the water. All right, number 4, Miss Carroll invested $1,200 into 2 separate accounts. They're both earning interest. Account A is earning 8%, account B is earning 11%. She gains $117 in a year. How much did she invest into each account? All right, so basically what we're looking at is, again, we have two variables. So I'm going to call X the money invested at 8%, where Y would represent the money invested at 11%. Now it says here she invested $1,200. So right away I have one equation, X plus Y equals 1,200. The second equation, we have to consider the interest rates. So the first account A, was 8% interest. We don't know how much she invested there, but we know the interest would be 0.08 times that amount. The 11% account would be 0.11 times Y, so 11% of this money, would give us a total of $117 interest. There's our system right there. Why don't you do this? Pause the video and pick a method to solve that system to find your answer. Hit pause. Do it now. All right, welcome back. You can see my result there. Now, the method I chose to use was graphing. $500 in account A and $700 in account B is what I ended up with. I'll show you what that looked like on the screen. I think you can see that now. I've entered my two equations here and found the point of intersection, which was 500, 700. So again, this represents the money in A, where the 700 represents the money in B. All right, I really like that graphing method. I think a lot of you probably do too, but you're free to use whichever method you're most comfortable with. All right, and here's our last one. Mr. Thornburg is using his slightly above average, and I might have been being nice, math skills, I'm teasing Mr. Thornburg, to assist the Olathe South Science Department. The chemistry teachers needed 90 liters of 8% hydrochloric acid for an upcoming experiment, but they only had 6 and 12% solutions available. How much of each type should Mr. Thornburg advise them to use? All right, so here's the deal. We know it says how much of each of the two types, so we know that it's going to have to do with the amount of the two varieties of hydrochloric acid. So I'm going to say X represents the liters of 6% hydrochloric acid solution, where Y represents the liters of 12% hydrochloric acid solution. Well, we know there's a total of 90 liters. That's the first equation. It says they need 90 liters. So I'm going to start out with X plus Y equals 90. That has to be the case. If you add the amount of 6% and the amount of 12, we got to add up to 90 for them to have 90. All right, now is when we have to consider percentages though. So how much of the actual acid is in the mixture? Well, the first mixture is 6%, so 0.6% of X is acid, and 12% of Y would be the pure acid. So 0.06X plus 0.12Y equals, we're trying to get to 8%. Now here's the most common mistake people make. They stop right there. Well, this isn't just a 0.08, it's 8% of what? Well, it's 8% of the full amount, so of 90, so times 90. Folks, that right there, that times 90 is without question the biggest mistake I see in all my classes on this type of problem. Again, why don't you pause the video, choose the method you want to use. This one could be set up nicely for a substitution. Maybe you want to do an elimination, maybe you want to graph, but pick your method and go with it. So pause the video now. All right, welcome back. It may not surprise you that I chose the graphing method. I really like graphing. And so I can see here, you can see I copied a picture of my graph here. I would have 60 liters of 6% solution and 30 liters of 12% solution. All right, folks, I know there's some challenges in this lesson. We'll work together on it. I hope that you've at least picked up a few things with this. You guys have a spectacular day.